Well, good morning. I think I got most of your exams, maybe one or two, and that's the next day now. So today is April 1st. So I'm going to lecture on Maclaurin and Taylor series. Okay. So, but first we need, so this is section 10.8. So we're gonna do Taylor and Maclaurin series. Okay. Suppose we have a function f of x that has an nth derivative. That is differentiable. Okay? And let's say we want to expand this function about x equal a. So we want to expand f of x about x equal a. So let's say, so we want to write it as f of x equal to n equals 0 to infinity cn x minus a to power n. So this is what it means. Now, the book uses an. It's very confusing to use a here and an here, and they are two different things. So I'm going to use cn x minus a to power n. So those are the coefficient. Lily, it's okay, honey. So this is Lily. It's okay. So this is gonna be okay, I don't want to stop the video now. C0, Lily, Nancy, honey, come take the dog. Plus C1, x minus a, plus C2, x minus a squared, plus C3, x minus a cubed, plus, let's say we have cn x minus a to power n, and so forth. Okay? All right. So if you see what is, so we're gonna do the notation that f to power 0 of a is nothing but f of a. We're gonna use that. Okay? And we're gonna use the other notation is fn of x. That means this is d of fn over dxn. So that means this is the nth derivative. So this is the notation we're gonna use here. All right? Okay, so with that in mind, so we have, let's put, we have f of a equals c0. We have f of prime. Okay, so let's take the derivative. F of prime. Okay, so instead of calculating f of a, so that's okay. And what is f of prime of x? F of prime is c1 plus all 0. F of prime of x, c1 plus 2c2 x minus a plus 3 c3 okay, times x minus a squared plus 4c4 x minus a cubed plus n cn x minus a to power n minus 1, and it keep going. Okay? So this is, I'm differentiating this polynomial here. I'm assuming this converge and the derivative exists and so forth. All right. So we calculated f of a from here. That would be c0, f prime of x. So let's do f prime of a now. That will be c1. Because you put a everywhere else, you're gonna get 0. Correct? So let's do f second of x. That is 2c2 plus 2 times 3c3 x minus a plus 3 times 4 c4 x minus a squared, and the other one is, so this one will be, and so forth. That's it. All right, so if I look at f second of a, I'm gonna get 2c2, and this will be 0, this will be 0, and so forth. All right? So now let me do f third of x, and that will be 2 times 3 times c3 plus 2 times 3 times 4 c4 x minus a plus, and if I do f third of a, I'll get 2 times 3 c3. Okay? Now let me do one more for you so you will see the rhythm here. So if I do f4 to power x, I'm gonna get, will be, okay, no, I'm looking here, will be 2 times 3 times 4 c4. And so, plus some other term. So if I look at f4 of a, that is 2 times 3 times 4 times c4. Okay? All right, so let's put everything in perspective. Let's put everything into perspective. So what do we have? We have c0 equal f of a. I have c1 equal f prime of a. I have c2 equal to f second of a over 2. I'm gonna write this as f second of a over 1 times 2. c3 is f third of a over 2 times 3, and that is f third of a over 1 times 2 times 3. And let's do the last one, and then I'll get f4 of a is 2 times 3 times 4 times c4, and that is 1 times 2 times 3 times 4 c4, and that is 4 factorial c4, and c4 is f4 of a over 4 factorial. So in general, we're gonna have Cn equal to Fn of a over n factorial. Okay? So that is in general. All right. So in this instance, we can write, so I can delete all that. Okay, and so now, so this one, this is the Cn. So the Cn are Fn of A over n factorial. Okay? So now we know what this is. So in other words, this one can be written f of x equal n equals 0 to infinity Cn xa minus power n. This is n equals 0 to infinity Fn of A over n factorial x minus a to the n. Okay? And actually this will be the Taylor series, which we will do in the definition in a second. Okay? All right. So you will see how to compute this one. All right. Okay. So note that if we let A equal 0, that means we do the power series extension of f centered at 0, then f of x can be written as n equals 0 to infinity Cn x to the n, and that is n equals 0 to infinity. The Cn are gonna be Fn to power 0 over n factorial xn. All right? So this is about a equals 0. If we let a equals 0, that will be about x equals 0, and this one is about the center x equal a. All right, so let's have a definition of Taylor and Maclaurin series. Okay? Let f be continuous and differentiable okay, at a point A of all orders. Okay? So basically we're gonna have continuous function and differentiable at a point at a point A. So basically if you take an interval, it's gonna be in an open interval that can contain this point A of all order, then the Taylor series, that means then the Taylor series, okay, of f at x equal a is f of x equal to n equals 0 to infinity Cn x minus a to power n, where Cn is Fn of a at n factorial. Okay? Now, to the Maclaurin series of f at x equals 0 is f of x equal n equals 0 to infinity Cn x to the n, where Cn is Fn to power 0 over n factorial. So this is the Taylor series. It's at x equal a is non-zero, and if a is 0, then we call it the Maclaurin series. Now these are very important later on in application in your engineering classes, higher upper math classes, and so forth. So you need to know this stuff, and let me do a couple examples. And so let me do now the polynomial. Okay? So All right. Okay. Let f be continuous. This is a Taylor polynomial. Okay. Let f be continuous in differential at a of all orders. Then we're going to have that the Taylor polynomial of f at x equal a is given by, we're going to call this as a Pnx, and that is equal to basically k equals 0 to n ck x minus a to power k, and again ck or fk to power a over n factorial. So this is so basically if you want the P1, you go from 0 to 1, okay, and so forth. All right. Here is an example. Fine. So this is the Taylor polynomial of f of x equal e to the x at x equals 0. So basically, looks like a Maclaurin polynomial. All right. So we're going to take a look at Pnx equal to the ck. So let's see, f prime of x equal e to the x, f second of x equal e to the x. So all the way to the nth derivative or k's derivative of x equal e to the x. So that implies fk to power 0 is e to power 0, and that is 1. So we got all of them. So, and sorry, here I want ck here, k factorial. Okay, so Pnx equal to k equals 0 to n ck. So what is ck here? Ck x to power k, and that is, note that here ck is fk to power 0 over k factorial, that is 1 over k factorial, because fk power 0 is 1. So that is k equals 0 to n x to the k over k factorial. So that is the polynomial, the case polynomial for the function and so forth. All right, any questions? Okay, so if you write this out, let's say we want the P1 of x. P1 of x is k equals 0 to 1 x over 1 factorial, and that is k equals 0, k. So if you put k equals 0, you get 1 plus k equal 1, you get x. So what is that? So that is a straight line. For x equal 0, y is 1. So it is a straight line like this. So this is P1 of x. All right? Okay? Now, if you want to do P2 of x, if you're going to do P2 of x, that is k equals 0 to 2 xk over 1 factorial. So that's factorial. So that will be 1 plus x k factorial plus x squared over 2. So you see that is a polynomial. Okay? And that polynomial can go like this. So that is P1, that is P2. And if you do the 3, they're going to go pass here, but it will go all the way. So they all pass at this point, because when x equals 0, note that when x equals 0, they all pass at this point 1. So let me give you a better picture. This is 1. So this is a P1 of x. And this is P2 of x. This is going to be P3 of x. And they all pass at this point. Why? Because when every term, when you put x equals 0, you get 0 except the first term is 1. So they all pass at this point here. Okay? So this is what we call a Taylor or Maclaurin polynomial. And that polynomial goes on and on, okay? So you just, whatever you want, so this is your polynomials. So you can do sine x. So for example, at home, try f of x equals sine x. Try it. Find the polynomial for it, okay? And so forth. I will upload another video tomorrow. So after the exam, I want to make this short. I just want to introduce the polynomial before we talk in details about the Taylor and Maclaurin series and how to find the Taylor and Maclaurin series for some basic function that we use all the time, like e to the x, sine x, cosine x, ln, and so forth. Okay, and then how we can do it by doing some manipulation at other points. All right, so in the meantime, I'm going to give you a few problems to do. Tomorrow, I will be here tomorrow during your regular class time. Okay, so the first class is at 10. Tomorrow is at 12:30, and the other one is 2:30. I believe. Okay, so I will be here tomorrow at this time for a Zoom session with you, live Zoom session. Okay. So again, let me say, if you have Pn of x equal to k equals 0 to n, and this is fk of a over k factorial x minus a to power k. So p0 of x is p0 of this is order 0. p1 of x, this is order 1, and so forth. p2 of x, that is order 2. So that means here n is 0, n is 1, n is 2, and so forth. Okay, now that we know that, at page 640, number 1, 3, 5, 7, and 25, 27, and 31. Okay, so that's your homework, and then we will talk about finding the power series for certain function. Okay, have a great day, and I'll talk to you later.